talk about today is cable characteristics. How does cable work? What are all us sneaky cable guys? What are we doing? Are we doing something that we can't do, or are we doing things that you can do, you just don't know about it yet? Well, you're going to know about it by the end of the presentation, because I'm going to explain exactly how the physics of cable works. It's not like you think. People have massive misconceptions about how our cables actually are working. All right, it's a little different than what you probably realize. We're going to start with this simple RLC tank type circuit, because it's got a lot of secrets built into it that we're going to use when we start looking at our cable, even though this isn't a cable. When this thing is in resonance, the voltage across the inductor and the capacitor are exactly the same. Now this only occurs when the circuit is in resonance, so it's a special condition, but the interesting thing about it is when the circuit's in resonance, everybody know about inductors, how they cause current to shift in time. Capacitors cause voltage to shift in time. The neato thing about high frequency RF cables is they magically don't shift current and voltage, which makes them really good for signal transmission. If I adjust this to reach resonance, the voltage is the same, but something else happens. I don't have any current or voltage phase shift at all in my circuit anymore. The circuit literally looks like 3 resistors now. Now, what can we do with that little piece of information? We can kind of come down here to our high frequency RF equation. Everybody probably understands the high frequency RF equation. One of the ones you can use anyway is square root of L over C, inductance over capacitance, is the impedance of a high frequency RF cable. Did anybody notice there's no phase attached with the impedance of a coaxial cable at RF? They don't say it's 75 ohm cable at 25 degrees or 45 degrees or 12 degrees. It's just a number, right? Why is it a number? Because the cable is at resonance at RF, the phase shift goes away. Just like in a tank circuit, same thing. So technically an RF cable is a special design that is theoretically used when the cable's in resonance, so there is no phase shift, voltage or current. That's very good for high frequency digital signal transmission and things like that. So in case you want to wonder why a cable is a 30 ohm cable, a 50 ohm cable, 100, it's because it's a pure ohmic number. We don't have to worry about phase shift. When we start going down in frequency, we notice something. And this affects our audio hobby quite a bit. What the hell with this? This is our impedance through our audio frequency range. This is 10 hertz, 10K, 100K, but look at this. Is anybody aware that the impedance of your cable at audio is going up like that? What's your impedance of your loudspeaker? 4 ohms, 8 ohms, up maybe 16 ohms, right? Everybody knows you're supposed to match load. You're supposed to put an 8 ohm cable into an 8 ohm load. Are we doing that? Does that look like an 8 ohm cable? 100 hertz, what's my impedance? Holy crap, it's way the hell up there. Mission control. Problem. Mother Nature's kind of thrown us a curveball. Well, we're going to find out why is our cable doing this when we go to low frequencies. And believe it or not, you can only mitigate it, you can't fix it. Mother Nature kind of is messing with our heads a little bit on this. Now the reason we start to see this curve go up is we start putting frequency into these equations, and the minute we start putting frequency in there and go out of what's called the resonant frequency range of RF, now we all of a sudden have reactance built into the cable. And that's what's causing this cable to have a higher impedance. If we look at our standard measurements for resistance, capacitance, inductance, when I'm measuring that cable at 6 gigahertz, 12 gigahertz, roughly 1 megahertz, what's the frequency point at which we measure the capacitance? Now this was actually swept capacitance to build these graphs, but in the Belden catalog, let's say you look up a capacitance on a cable and it says it's 17.3 picofarads, and you're looking at a MATV, CATV, high frequency coaxial cable. Where do you think they measure that capacitance? What frequency? Really high or really low? What do you think? He says really high. He is high. Because the answer is really low. They measure it at 1 kilohertz. Seriously. All the RF measurements for capacitance are measured at 1K. Now, why did they pick that? Well, first of all, it was developed for MIL-C17D, the mil specs that you oftentimes use when you build cables. But in the old days, they used to use tubes. Tubes do not like to run an RF reliably. It takes a lot of energy to run a tube at high frequencies. So the guys said, you know, capacitance is the same with respect to frequency, so why stress our equipment out? Let's just measure it at 1K. Now today we could measure at 1 megahertz or whatever, no sweat. But in the old days, the standard was 1K, and we've just kind of stuck with that. These numbers are from a cable that has multiple pairs inside the same cable. So you have a cable that's got an outer pair and cables that have what are called inner pairs. And they have different capacities. The inner pairs have higher capacitance. Why? Because they have a whole bunch of metal around them. The outer pairs just are sitting on top of the inner pairs, and then they have air above them, or basically plastic. So they'll have a different capacitance level. So ignore this. This is more like our audio cable here, where we see this nice, super flat capacitance. But that's good, because that means we don't have to worry about capacitance changing. So when we look at some of these other formulas, we can be confident that if we have a capacitance number, it's not going to change. Now, if we look at the inductance, what do you notice about the inductance? It goes along pretty good, but then all of a sudden it gets all saggy, weird at high frequencies and starts dropping down. And quite a bit, actually. So if you're trying to measure a cable plus or minus 1 ohm, you're obviously going to be off quite a bit, unless you know the frequency you're measuring inductance at. But then, why is that changing? What's going on? Is it getting tired because it has to go way up here? What actually is happening is the skin effect is predominantly starting to influence the inductance measurement, believe it or not. How can that possibly be? Because what's inductance determined by? How close two conductors are together. It's called loop area. So if my conductors are real far apart, I have a very high inductance cable, a lot of loop area. As I bring those conductors closer and closer together, the loop area gets smaller, my inductance goes down. And you look at it and you say, well, Galen, you're not bringing those conductors together, they're just sitting there, right, during the measurement, so why is it dropping? Well, because that happens to be a super high enough frequency where all the current is leaving the center of the conductor and it's migrating to the outside surface. When that current migrates to the outside surface on both conductors, the wire thinks it's closer together because there's now no current in the middle of the wire anymore, and the distance is the average. Mother Nature likes to average stuff. All right, it kind of does a group type thing. So it basically looks at the current on the inside of the conductor and the outside and averages it and says, okay, my distance is somewhere not on the outside of the conductor, it's somewhere down in the middle of the conductor a little bit. But when you get rid of that at high frequencies, you're stuck with the current only on the surface of the wire. Now my loop area is smaller. When I make the loop area smaller, guess what happens to my inductance? It drops. Now we have a magic bullet that can fix this problem, so we don't have to worry about what the inductance is doing when we measure our audio cables, and I'll talk about what that is. So you kind of got to be careful with what inductance is doing when we measure our cables. This is some examples of a couple of cheaty little easy ways to determine what the impedance of a cable is. If you look in the Belden catalog, we'll measure the capacitance for you and tell you what that is, 17.3 picofarads, whatever it is. It's measured at 1K, it's going to be the same at RF. We'll actually also show you what the velocity of propagation is in that particular dielectric. But to do that, you have to have some really expensive equipment and do what's called the resonance method. And basically you put in two different RF frequencies and do some tricky math, and it will come back and say what the velocity of propagation of that particular dielectric looks like in that cable, and we'll put that in the catalog. If you multiply those two numbers together and divide it into a constant, 101,670, that gets rid of all these other scary symbols, so it makes it simple, it will pop out an impedance. Okay, so it's saying it's 92.7 ohms, all right, or excuse me, it'll say it's, in this case, 89.6. The square root of inductance divided by capacitance gives us 92.7. Not the same, but it's kind of close. Now there's another method called open short method. And this gives you an impedance if you take the square root of the open times the short measurement. The velocity of a DC signal is 0. Well, Mother Nature doesn't like to go from some crazy number up here over and over and over and then straight down to DC when she gets there. Mother Nature likes to creep up on stuff. So what Mother Nature is doing is it's taking the RF limiting velocity, in other words, the speed of the EM wave at RF when the cable is under what we call resonance. In other words, as fast as the signal possibly can go in that particular dielectric. But as we drop the frequency, it wants to go down to DC and hit 0. Depending on where you start up here, determines kind of the shape of the curve before you end up at 0 down here. Now people that are, how many people in here listen to wire and say, oh, this conductor sounds different to me than another kind of wire? We have some people that agree with that. Well, here's something that might suggest that's valid. Here's 9269. Notice the curve is different than these other three, which are copper. They're bigger or littler coppers. That's because you see them lined up a little different, because the dielectric property out here is different. But this curve is different. That's going to affect how a cable works, and you can measure it and you can see it. It's not the same. Why is it not the same curve? Because it's a different kind of conductor. If I put gold in there, silver, aluminum, you will see different shaped curves based on the characteristics of that metal and how it behaves. Now let's cheat a little bit, or uncheat the curve, and look at it and see what it really is telling us. This is RF up here. Something I want you to notice, people say, well, if that's RF, how come the velocity of propagation is so low? It's 50% of the speed of light in a vacuum. Is that a problem? Well, it's not a vacuum, okay? And it is a composite dielectric. Even though the conductors in this case are insulated with FEP, someone that's here will say, well, it's 1 over the square root of E, and I know E of Teflon is 2.1 because I'm really knowledgeable, and that's 69%, but you're way below 69%. That's because there are other parameters in the cable that Mother Nature averages out. She says, okay, you got some FEP, but you also have some other stuff going on, so all I'm going to give you is 50% of the velocity because I'm going to give you a composite structure dielectric propagation. This is one design, and you see its characteristic slope. This is another design. When I tweaked that equation that I showed you in the previous slide and showed you kind of tweak this stuff a little bit, but notice you can only tweak it so much. Why? It's going to go from RF limiting velocity, based on the design, it's going to go to 0. Here's 10 hertz, look at my velocity, I'm like at what, 4 or 5%? Well, that's pretty close to 0, you guys, so it's definitely going to frickin' 0. The velocity of propagation at DC is 0. So that's where Mother Nature says we're going to go. We can't change this end of the curve. 0 is 0. Mother Nature says that's where you're going to start. Now we can sort of change where we end up. And based on the design, I can change this number to 60, 40. But to do that, I have to change certain cable parameters that may or may not be the right thing to do. It could cause more harm than good if I go too crazy with it. So the cable designers sort of have to work with this to figure out how not to make a problem worse when they're trying to fix another problem, because it's all interrelated. This cable is actually a better design than this one. Why? Because the velocity of propagation through the audio range, here's 10,000 hertz. We'd like the speed of our signal at all frequencies to be exactly the same. It's not. But the physics of how this works won't let us send signals down the cable at all frequencies exactly the same. That's called group delay, okay? It basically is just a description of how signals vary based on the frequency. And most people aren't even realizing how many people thought audio cable did this. How many think this is a new thing? Seen this? That's how it works, guys. And you can't cheat the physics. We can bend it a little bit in the middle, but I can't cheat the fundamental nature of how it actually is working. So that's what cable guys kind of have to struggle with. Is this new? Am I sneaking this in at the last minute? Just discovered it before I came to the show? Probably not. I don't look that smart, I hope. Those curves were done in about 1920 during the Bell Telephone Labs. Okay, this stuff's been around a long, long, long time, but it's been kind of secret in the audiophile community. But anybody that's in the scientific community, the communications community, including the Bell Telephone Company, when they were developing what? Telephones, right? They had to figure out a way to make the voices go from grandma to your sister such that they were intelligible. Those lines were so long and the wavelengths got so distorted going down the cables that it didn't sound like grandma, it sounded like somebody from the Chipmunks. Because it was distorted literally by the speed differential across the frequency range. And they were basically interested in things around 1 kilohertz because that's where your ears are pretty much the most sensitive. So they would do things in the 1K range, all right? But again, you see the same fundamental characteristic. Now let's look down here a second. We got a phase angle. Remember I told you the phase at RF is 0 because we're in resonance and the phase angle disappears? In audio, we can't do that. Guess what happens? When you look at a cable sitting in an audio system, say a speaker cable, and you measure it, the phase is 0 out at RF, that didn't change. But what happens when we get into our audio range? We're like at minus roughly 45 degrees. What is a negative 45 degree phase angle? That basically describes, mathematically, anyway, the imaginary number minus J, a capacitor. So we know our audio cables are going to get more capacitive as we go down in frequency. Capacitors store and release voltage, all right, at a different time. That's not good. We don't really want to store our energy. We're greedy. We want it right when we want it. But the physics is saying, can't have it, sorry. You go low enough in frequency, your cable is now a capacitor. So we have that going on. And we'll start to see real cable measurements that support exactly what these theoretical graphs show. These were all done with mathematics, by the way. These weren't real cables, but I'm going to show you real cables measured. And here we go. This is the open short method, and everything's going to match up with everything we've talked about up to now. It's not going to, it'll all fall right in. The open measurement, okay, is when the cable is capacitive at the low frequencies. As you go up in frequency, the capacitive nature of the cable becomes less. When we short the ends of the cable, we have a very high or low resistance instead of a high. This is high to low. This one's low to high. It's kind of the opposite. So as I increase the frequency, the resistance keeps going up, up, and up, and up, and up. And that's because of the skin effect, proximity effect. All that stuff gets captured in that measurement. It can't escape. You can't really cheat. All the tertiary elements that audiophiles like to talk about that may be in there, do I hear it? Don't worry about it, because when I measure this, it captures all of that. It captures everything. It's a composite number. Now, what you do is you take this number, these two, and you multiply them together. You take the square root of it, gives you an impedance. At 20 hertz, it's saying the impedance of our cable is 509 ohms, you guys. That's a 10-gate zip cord, basically, there. Everybody realize the impedance of your cable's that high when you're trying to put it into your speaker that's supposed to be 8 ohms? Is that a, quote, impedance-matched network? Do you think there might be some arguments between the cable and the speaker and the amplifier when you have that big of a difference in the impedance of the cable? I say maybe. Anybody knows about transmission line theory says anytime you don't have a matched line, you're going to have an argument about who's on first, and we do. But the physics of how this works, everybody, will only let you do so much with this. We can improve it, but I can't make it go away, at least not on this earth. Now, if you look at the phase that's connected with these two measurements, we have another equation. You take the open plus the short divided by 2. That'll give the phase angle of that impedance magnitude. We don't want that phase angle to be anything but 0, right? We like it to be a pure resistive number. So if we're off of our impedance, at least let us, thank God, be resistive. No, we're not. We're at minus 40 degrees at 20 hertz. Not quite 0. If you get down close to 0, it's going to want to go to minus 45 degrees, which is a capacitor, basically. In other words, our cable is a long capacitor. As we go up in frequency, all of a sudden our phase is getting pretty close to zero. Those graphs said it should. And it is. These are real measurements off real cable. This is not theoretical guy with the calculator sitting at a desk. This is real measurements on the stuff we use every day. So we see that it matches the theory. So we're starting to get very resistive as our cable goes up in frequency. That's good because our ears are very sensitive to phase as frequency goes up. That's what gives you image stability when you listen to speakers, you know, where everything sounds like and funny. That's all got to do with phasing information. As we go down in frequency, the phase in the cable gets pretty bad. But our ears don't hear low frequency phase very well. That's why, how many people have subwoofers? Anybody? Now, what's the worst thing about your subwoofer? It's not selecting your crossover frequency, it's adjusting where the phase is on your woofer, right? Everybody know where that phase knob is? You're trying to match it up? Because our ears can't hear phase, and we're always thinking, every day we probably fiddle with that knob, don't we? Because we think the phase ain't quite right. It messes with our heads. So a lot of us will use DSP that can hear better than we can and let the machine adjust the phase. And if you're patient or disciplined, just don't mess with it anymore. So phase is hard for us to hear low frequencies. So even though the phase is getting pretty bad, it's fortunately doing it in a frequency range to where it's not as audible as at the high frequency. So we like to see the phase get less as we go up. That actually is working in favor. So everything's not terrible. Now when we measure the swept resistance of the wire, that'd be the first part of the open short. So this would be a short part of the measurement. Does it matter? You can't hear that. Well, this is a zip cord. This is a 10 gauge zip cord. All right, typical, good enough cable. Supposed to be the same as everything. No different. There's no difference in these cords, by the way, right? That's what you're told. Here's 7,500 hertz. The minute you get above 7,500 hertz, the swept resistance of that cable starts to go nuts. That's the proximity effect, skin effect, DCR, the conductor, all that stuff rolled into that measurement. It's all starting to look very different. Now, if you do some design changes, which your cable designers should be doing for you, and show you it's better with this kind of measurements and testing, I've got this flat now, clear out to 20K. The problem is still there, but it's above where some of you guys, I can't hear that high, but somebody might. But I ameliorated the problem by changing the design of the cable. So we can adjust some of this stuff to our advantage. Now, has this been done before? Is this stuff new? I wonder. Maybe I just went to Nelson Pass's secret laboratory in San Francisco and stole all this information from him, but then probably not. Maybe I just read his paper that was written about 50 years ago. And I'm not joking. This was way back when. He wrote an article, and what on earth do we see? We took all the contemporary cables at a time, and he started measuring them, and he basically charting the first part of the open short impedance test. He didn't know that's what he was doing, because he wasn't a cable design engineer, but he measured the first part of the test. He called it series impedance. We know that that can't be true, right? Because an impedance reaches a resonant frequency and remains stable no matter where you go once you get above that resonant frequency. But if we look at these graphs, same as mine, they're going up, up, up and away. So that's not impedance yet. He didn't know that you have to combine it with the capacitive reactance, multiply them together, take the square root of it, and that would be the impedance of that circuit. But he did get the first part right, and he was one of the first people to say, hey, these cables are really different based on the design. That might have something to do with how my amp is behaving into them, how it makes it sound playing through that cable, and how it sounds hooked up to your speaker. So this was some of the first early, credible, in my estimation, repeatable measurements that show cables aren't the same. They're going to have different impedances, some higher, some lower. It's going to affect how the amplifier behaves and how it loads to your speaker. Are we listening to the cable though? We aren't, are we? Last I checked, cables don't play music. They make music go through them, but they don't play music. So we're listening to a network. Your amplifier is looking at a reactive network that's part the cable, part the speaker. When you change the cable between them, you change the reactive characteristic of how that amplifier plays into a reactive load. An amplifier is only linear or goes linear into a resistive load. our speakers aren't resistive and our cable's not resistive. So we have some network incompatibility, shall we call it, going on. Now, this is the prettiest graph I'm going to show you all day, so look at it and enjoy. It's got nice blue colors. All right, kind of looks nice, pretty. What is it? This is a 100 ohm cable. These are 405 measured data points by yours truly. And it's an examination of the reflection characteristics at RF. We're going to look at this, and then we're going to consider what happens at low frequency analog and kind of see what's similar and what's not. What do we have? This is basically a measure of what's called return loss. Now, if you take a 75 ohm resonance type cable and you terminate it, we've already said it's resistive, right, when it's at resonance. So when you plug it into a NIC card, what is that signal being dropped across? It literally is a 75 ohm surface mount resistor. Don't have to worry about phase shift, right? It's all resistive. So a coaxial cable, SPDIF or something, is going into a resistor. This actually goes into a 100 ohm resistor at the other end of the cable. That's a termination, and that works at RF because we've already said there's no, quote, phase shift. Is that true? If that were true, why do I have some of this signal reflected back off of the load? Because if the cable was truly 75 ohms resistive, nothing would reflect off of a resistor. It would all be dropped across the load, but it isn't. So this is really a measurement of how much we've screwed up making the cable. I mean, it literally is that. So in other words, our coaxial cable is not always resistive. Even weirder, if you take your finger and you look at this 100 ohm load, and we follow it down here, every data point on that is 100 ohms, yet the amount of energy that's reflected, this being better, this being worse. But you're saying, what the hell? You mean on a length of cable, sometimes I'm getting almost no reflection, and at 100 ohms, sometimes I'm getting tons of reflection. But it's all 100 ohms, how can that be? Because impedance is what? It's a vector, right? You have a magnitude, and you have an angle. It just so happens this magnitude here is mostly resistive. This magnitude over here, that's still 100 ohms in magnitude, but it's at a highly reactive phase angle, so I get a lot of reflection off the load because the load says I hardly see any real resistive energy here to accept, so I'm going to let it bounce off and go somewhere else until later when it's more resistive. Even funnier, if you come to here and I go up, take that data point, come over here, it's a 95 ohm cable. I come up to here and it's somewhere around 110 ohm cable. But all three of these different resistances, including the 100 ohm cable in the middle, all have roughly minus 30 dB return loss. Exactly the same return loss, but I have three different impedances. Why is that? They all have roughly the same resistive magnitude, even though the impedance vector are three different impedances. What does that mean? I could actually make a cable that is lower in impedance that can have less return loss than a cable that's at 100 ohms. Pretty crazy stuff. But this is how it really works, you guys. These are real measurements made on real cables. So it's not theory. We don't make cables that are 75 ohms. We try as hard as we can. And let's take a look at this and think about what's going on with our audio cables now. PS Audio had this cool little graph that shows music. This might have been my Nickelback CD, or Jethro Tull, or REO, because it got up to 1,000 watt peak anyway. But if you let this run over time and let it be spectrally filled up, if you listen long enough, what you would find is the ratio of your energy at the low frequencies, 100 hertz, relative even as low as 2K, the differences are like hundreds to one. In one case it's 1,000 to one. We got a ton of power at the low frequencies, and we're trying to jam this through a cable into our speaker. And our speaker is what? We just learned our speaker cables at the low frequencies are a pretty high impedance, right? Certainly not even close to 8 ohms. They're in the hundreds of ohm range. Yet at the same time, we're trying to put the most power into the load at that frequency with the largest mismatch. So it's any wonder when you change from one cable to another, and hear differences in the bass response and things. This is why, that's where the impedance match is worst, and that's where we're working with the most amount of energy. That's where our reflections off the load are the worst. As we go up in frequency, we already learned that our cable looks more resistive. We don't have a lot of power to lose at the high frequencies either, but that's fine because it's into a more resistive load, so we have less reflections or incompatibilities as we go up in frequency. So that's in our advantage. So here's what our speaker load kind of looks like. This is a ported speaker, so you get the double humped trace. Matters worse, look at the reactance, the dashed line. That basically is telling you where energy will not be accepted very easily. As a matter of fact, they have an equivalent series resistance kind of calculation that they do like in stereophile. So basically they take this value, they come straight up and they combine it with that value and say, well, this value is really not here because of this, it's really more like down here. So they kind of superimpose the two on top of one another and tell you what your amp really thinks it's trying to drive at that particular frequency. And it's always lower than this value. As long as this value is above it, it's going to tell you this impedance is really, at that frequency, it's not really the impedance you think it is. So in other words, it's going to drive your amp nuts. But this is 18 ohms, roughly, peaks here and here, nominals kind of down. But that ain't even close to our cable. Our cables, you know, you won't believe me, we're going to see in just a minute, our cable's quite a bit higher impedance than that. Here is the phase over here, and it still matches. It's saying that my cable, two different designs, is still fundamentally acting like a capacitor the lower I go in frequency. It's looking like it's a capacitor. That's what this 45-degree phase shift is telling me. As I go higher and higher in frequency, I'm approaching the 0-degree phase shift. That's real cable measurements again. So that's what cable really does. Higher in frequency we go, the more it looks like a resistor. Not a perfect one, mind you, because we already saw in the SRL graphs, the pretty blue graphs, that we can't quite do that even though we try. But look at the impedance of the two different designs. This is roughly 525 ohm cable. Damn high. Even at 1,000 hertz, we're at 200 and some ohms. I can make design changes and cable engineers can look at this and say, well, let's improve this. And we got that down to roughly 275 ohms. In other words, roughly half. Now, one thing you'll also notice is look at the difference in the phase. Even though we're the same here and here, this spot in the middle has phase differences, and that's going to affect how a cable images and how things sound in front of you. You might listen to a speaker or change your cable and say, the image is way back there, or it's way in front, or it seems like a tire, or the other instruments around it don't seem quite as clear. Well, some of that has to do with how the cable phase changes what we hear when we stick one cable in versus another. There are differences in measurement. This isn't made up. This is how and what they do when you actually do the real, honest-to-God measurements. Here's another example of some different cables, okay? Check out this. We got a cable that's over 1,000 ohms. Then we have some cables down here, they're in the 600 ohm type range. Those are cables that were made from some Bell telephony type specs and things. And like this is 1310, this is 1313A. All right, this is 10 gauge zip cord. This is an improved zip cord that's wired star quad, and if you wire it in a star quad configuration, I can drop the impedance significantly. So we've done some design changes at Blue Jeans to kind of try to improve this low frequency difference. All right, and then we have some Series 1, Series 2 impedances, okay, on there. But there are differences in these cables. They definitely are not the same. Oops. So that's kind of the end of the presentation, and the question most people have, right on the bottom, half of you are going to say it matters, half of you say I don't give a damn. It's different, but I can't hear it. It's definitely different, all right? But does it matter? The only way you know is to borrow cables, put them in your system, and see how your amp speaker cable combination sounds to you. If you try various different cables, you might have a cable and a speaker that's very resistive in nature, and some speakers are pretty resistive, like Maggie's. So when you change cables on magnepans, you won't notice as big a difference as you will on more reactive type load speakers, and that's why there's not that big argument between the amp and the load, and the cable's not aggravating it. So you can actually use a lesser expensive cable and still have really nice sound quality. If you have very aggravating situations like Dynaudio C4s or other cables that are highly reactive, you will hear bigger differences on those types of products when you change amps and change cables, or both. And it's all based on the physics of how all this is kind of rolling in together. Any questions? Did you guys learn anything? Did you realize this is how cable actually works? This is how it really works, guys. This is not, and at our site, we don't have adjectives that talk about sound, but we got plenty of stuff that talks about the physics of what we're doing and how we can do it. And there's a lot of cool stuff here that all the cable design engineers can work with. The guys who make speakers, they have their own secret formulas and things and laws of physics they have to abide by as well. I'm just kind of talking about what the cable design engineers have to work with. So now we understand why our cables at high frequencies drop in impedance. We understand why they go up at low frequencies, because if VP is going to zero, that makes our impedance go up. Okay? We know how to properly characterize an analog type cable at low frequencies using open short, so that's a realistic way to help us understand what our cables are doing. We know what those numbers are comprised of. We have to have R, L, and C. When measurement gets RL and C, or RL and the swept characteristics, the other one gets the X sub C, or the capacitive characteristics. So we roll all those together, and that generates our impedance. So I know you could be anywhere but here today. I want to say thanks for coming. I hope I didn't confuse you too bad. Pardon me? How much do I spend on cable? Only until you can't hear it anymore. I mean, we have a variety of cables starting at we have 1310A, 1313A, and then we kind of go up the line. So there will be a point, depending on your amp and speaker, the differences will be mitigated where it'll be hard to hear a difference. It all depends on the network interaction of these products because of the reactive nature of everything. So for me to say you should spend $1.95 and you should spend $7 because he looks richer than you, that's about as close as I could get to honestly answer your answer. In other words, I can't. Stick with your budget. Listen, you can borrow a higher end cable for free for 30 days, stick it in there, borrow the most expensive one we got and compare it to the one you can afford and see if you can hear a difference. If you can't hear a difference, you're done. Your system's kind of working really nice. If you can hear a big difference and you think it's a component level improvement over a new amp or a new DAC, then you might consider saving up on the side for better cable. Not everybody is going to get the same impact buying these expensive cables. It all depends on how your amp and your speakers work. So some of us get lucky and don't hardly hear any change. That's a good thing. Or you get lucky and you find a cable made not by us, but somehow agrees with your system better, and it might be cheaper. That's a good thing. So there's no speaker here for everybody, and we don't make cables for everybody, but I make certain estimations as how to make a cable that should sound good for most of you. But again, due to the complex nature of how this works, I can't satisfy every single situation because of how the physics lays out. I have to purposely change these parameters with the expectation that for the majority of users are going to be better. And if I can't show us better in the measurements, why the hell should you believe me in buying them or even borrowing them? I can show you these cables that significantly get better electrically as you go up our brand, for instance, but that still doesn't describe how they're going to sound and how they're going to interact with your amp and your speakers. So I wish there was an answer to say if you have these numbers, it's always going to sound better. That's not true. It's just, it's not. And I think you can see why. Cryo orients the metallic structure so that it reaches a maximum level of strength because it removes the stresses in the draw process, but it's not ever been proven to affect the resistivity or the other things. All right, so it was developed basically to make metals stronger, not sound better. It does definitely make them a lot stronger. Like if you take a copper wire and you cryo it, the tensile elongation of it is going to be really good. It was developed for the space program and defense and things like that because they didn't want the wires breaking. So they figured, we figured out if you align these molecules up correctly, the wire's a hell of a lot stronger before it breaks. So it does work, but I don't know and can't say, in my estimation, I've ever heard it make a wire sound better. Nothing that I'm aware of you can measure other than physicals. You can measure physicals. There's a lot measurable, but it won't show up here. It's invisible. As a matter of fact, all of our cables, if you measure R, L, and C with our 3 different copper offerings, TPC, ultra pure OCC, and OFE, and all of those, the R, L, and C in the same design are exactly the same. Where you can see differences here and there. Now remember, those are all copper though, so they're all kind of in the same family. So when we do the swept resistance, when we measure when we measure these kinds of things, since they're all copper and the design doesn't change, and I only change the copper, they're all going to look identical as far as the RS. It doesn't show up. But everyone listens to it and says, you know, this is different. I can measure a very small difference in resistivity. It's small, guys. It's less than 2 or 3%. It's there, but it's not very big. So all we can do is say, guys, we measure them the same. We use them in the same design. Borrow them and listen to them and see what you think. Are the ultra expensive, exotic, more expensive OFE coppers and things worth it? That's all we can do is be transparent. But unfortunately, I can't show you a number to tell you why. I wish I could, but I can't. Okay, do we do listening tests? Yes, we have hired beta testers to listen to all our products. Yes, the listening tests are almost conclusive. They feel that the OFE copper is a softer sound than the TPC or the ultra pure OCC. All right, so we do have listeners that do report the differences in the coppers, for instance. So now the TPC and the silver plate TPC are closer together in sound quality. Most people feel that the SP TPC has a more ambient, open sound. It's just enough to make it more enjoyable to listen to. All right, and this is over many sales. As a matter of fact, the reason I put silver on it was to make the tin lead-free solder flow at a lower temperature so it's easier to make the assemblies. That was the whole intent of the silver. But when we sent it out to our beta testers that had already had the older design, I was actually going to phase out TPC and try to use just a silver plate. All the beta testers said, no way, you got to offer both of them. They definitely sound different, and the silver plate is making a difference in the sound. And I'm like, no way. Put them in my system and they're right. It does sound different than just the straight TPC, even though the silver plate is only 40 microinches thick. Okay, but everyone's like, dude, and this whole project, you guys, when I worked at Belden, my job was to make sure these high-end, super good electrical cables sounded no better than our standard fare. My boss at the time said, Galen, you can't prove that high-end cables sound better until you know they're really better. Make them, measure them, and if they're not measurably better, then I'm not going to let you do this. So until you can measure them and prove that you make better cables, there's no way it can sound better. Do you agree? And I said, yes. He said, okay, go figure out how the hell to do it, because it's going to be hard. I took them home, and I had Belden 1313A, 1694A, all the standard, don't need to be better than 10 gauge, twin axe, right, or whatever, zip cord. The difference was astounding. I went back to work and said, Doug, I ain't taking these out of my system. They sound a hell of a lot better. And he's like, well, okay, and? I said, well, our market is large industrial type customers or even large NAB studios, things like that. In other words, they buy a lot of product. He said, the consumer market's not us. I said, well, what if I retire? You manufacture the cable to my specs. Blue Jeans manufactures and sells the assemblies. Would that work? And they said, well, if that's a way to get to people that are really willing to pay for analog cables that are this good, that are very expensive to make, because they're so time consuming, if your customer base feels it's worth it, go for it. Well, that was 5 years ago, here we are today. So that's the honest to God truth, is the whole project is supposed to prove why we shouldn't be here, and it made me quit, and I am here. And I have all the cables in my system, and I love them. So. And this is why, though, they are measurably better. But that doesn't mean they're going to sound better, right? You still have to listen to them. But to say they're not different is not true. They are different. And you can show that with industry standard test procedures. So there's nothing sneaky here. These procedures have been done for decades and decades. So everything's up and up. Even Nelson passed it the exact same measurements almost 50 years ago. So he gave me permission to use this slide, by the way. I called him up and asked him. He said, dude, where did you dig that out? What the hell? So I'm going to make you famous at AXPONA. So I think you all know who Nelson Pass is, right? He's the amp genius. Yeah. Any other questions?
Nelson Pass is the amp genius. Yes, I agree with you.
Yeah. All right, I think that's it, everybody. If you have any questions or think of something, we're just right over here, so I'll be happy to answer individual questions or whatever you want to do. But so did everybody have fun? Did everybody, was this worth it to you? I mean, was this kind of something you don't really see with cable? Did it benefit you guys to kind of know how this is all working? We were trying to decide if we should even do this because it's such a controversial subject. And I said, you know, as long as we show it's really happening, I think people will really enjoy it. And this is really what is happening with our cables. So, thank you.